Coming back to combinations, combinations are nothing but the number of ways we can select objects without worrying about the ordering of objects. Let's take an example. I have 5 books: physics, chemistry, maths, English, and biology. Let's see in how many ways can I select 3 out of them. One selection would be to choose physics, chemistry, and maths. This gives us our first combination. Another selection would be to choose chemistry, maths, and English. This gives us our second combination. Yet another selection would be maths, English, and biology. This gives us our third combination. Similarly, we could list down other selections as well. You can take my word for it that we will get 10 such selections. Before we move on, let's take a look at how we calculate the number of permutations for 3 objects from 5 objects. You could of course use the box method, but here is another way we could do it. I can first select 3 objects from 5 objects. I can then arrange the selected objects among themselves. And the number of ways I can do that will be my number of permutations. We have already solved the first piece of this puzzle by listing down all possible selections of 3 books from 5 books. Now we need to find out how we can arrange the selected objects. Let us have a look at the first combination, which consists of physics, chemistry, and maths. I can arrange the books in the order physics, chemistry, maths, or I can arrange it in order physics, maths, chemistry, or maths, chemistry, physics, and so on. I can have 6 such arrangements. But hey, isn't this the same as arranging 3 objects all at a time? That can be done in 3 factorial ways. In fact, this will be true for all the 10 combinations we saw previously. Hence, my number of permutations can be given as 3 factorial plus 3 factorial plus 3 factorial until 10 times. Basically, 1 3 factorial for each of the combination. This is nothing but 3 factorial multiplied by the number of combinations I got. Until now, we were working with 5 objects and 3 positions. For a more general case of n objects and r positions, it is easy to see that instead of 3 factorial, I will have r factorial. We have seen that we can write the number of permutations of n objects when taken r at a time as npr. Actually, number of combinations is denoted by a similar notation, namely NCR. It stands for number of ways to choose r objects from n objects. This can be written as NCR equals NPR divided by r factorial. Now we can plug the value of NPR that we derived in the previous section, which is nothing but n factorial divided by n minus r factorial. Finally, we have the formula for the number of combinations. It says the number of ways I can choose r objects from n objects is given by n factorial divided by n minus r factorial r factorial. This result is the most important result of this entire chapter. We will be using this again and again to solve almost all kinds of problems. Let's look at an example that uses this result. In how many ways can we give 3 candies to 10 children such that one child can receive only 1 candy and the order in which the candies are distributed doesn't matter? We will use the formula for NCR to solve this. Actually, let's do a quiz. What do you think will be the values for n and r in this case? Is it n equals 1, r equals 1? Or n equals 3, r equals 10? Or n equals 10, r equals 10? Or is it n equals 10, r equals 3?